Good morning. So, in the last lecture, we have seen how the concept of the solenoid movement can be used to design a analog DC instrument, okay, which will it's a analog DC indicating instrument such that it will give it on a dial, it will give a deflection theta, okay, that will be proportional to the current supplied into the instrument, okay, and this is a DC instrument, okay, and we have seen that and we've seen that this instrument can be used to measure various electrical quantity, primarily current, and using the relationship between current and other electrical quantities, it can be used to measure voltage and also the resistance. So it can be used, the PMMC instrument can be modified and calibrated to directly function as an ammeter, as a voltmeter, or as an ohmmeter also. And in this lecture we'll be looking at all these different applications, the modifications that can be made to make the ammeter work as a to make the PMMC meter work as an ammeter, voltmeter, or an ohmmeter. Okay, so we have seen in the last class that if you have a PMMC meter, okay, and a current I passes through that meter, then there is a deflection theta that is proportional to I, okay. Something like Gi will be equal to K theta at equilibrium, okay, and the same concept can be used to increase the range of the DC ammeter. So it was seen that the springs that were there, the control springs that were there in the basic PMMC meter, and the other wiring that was there in the PMMC meter, they can tolerate only a small amount of current, okay. So it should mean that the meter current IM that flows through this meter needs to be less. However, if we want to use it to measure a current I being much less than IM, or rather not IM, I being much less than the maximum current IFSD that the meter can tolerate, okay, then you can achieve this by connecting a low resistant shunt RSH in parallel with this meter. Now if RM is the meter resistance, you have RSH being much less than RM, okay, and now which would mean that a majority of the current passes through this shunt, and a small part of the current IM passes through the meter. Okay, now let's get into the mathematics of it. Okay, so it's quite easy to see that the voltage across this meter and the voltage across the shunt is the same. So the current relationship is given by this, okay. Now if IM is the current passing through the PMMC meter, and thus proportional to the deflection, then from this we can easily see that the total current is related to the meter current using this relationship, okay. Okay, and this you can use this shunt to increase the range of the meter. Okay, you use a suitable shunt and a suitable range can be increased. Okay, and the sensitivity of the meter is now is given by gi is k times theta. Okay, and in fact it's not even like this. So g into what you have is gim is k times theta actually. Okay, and you want di by d theta, so this would be di by d theta is k by g times this thing. Okay, times this relationship Rm by Rsh plus 1. Okay, so this would mean that the sensitivity of this meter is solely dependent upon this magnetic strength B, the coil dimensions given by this N, L and D, and the spring constant K. Yeah, so you would have the sensitivity d theta by di being dependent on the strength of the magnetic field, the dimensions of the coil and the spring constant, and of course this ratio between Rm and Rsh with anyway are constants. Okay. Note that nothing that is external to this circuitry figures out in the sensitivity function. All of these parameters can be assumed to be constant. Okay. Now, however, there is one thing that we are missing here. So as the current flows through the PMMC meter, okay, meter's coil, then the coil is going to heat up, and this change in temperature is going to cause a change in resistance. Okay, and since different currents, so there is an Im flowing through the meter and an ISH flowing through the shunt resistance. Okay, it is possible that these two resistances Rm and Rsh, okay, can suffer different temperature changes. So this can be delta T1, this can go by delta T2, and which would mean that the resistance Rsh can change by some factor, Rm changes by different factor. Okay, and due to this the resistance changes being at different rates, then the multiplication factor can get affected. Okay, so what we should do now is we should be able to have a mechanism where the resistance change, even though there is a temperature change, now that can't be avoided because large current needs to flow through the shunt resistance anyway. Okay, so the temperature change may not be avoidable. However, the resistance change can be avoided if a appropriate material is used for the shunt resistance. Okay, and therefore for temperature configuration, okay, we can have a high value swamping resistance, okay, and a low temperature coefficient shunt. Okay, so we are adding a swamping resistance Rs, whose resistance is 20 to 30 times the value of Rm. So this would mean that effectively the Im that flows through this branch, okay, goes down. Since IM goes down, which would mean that the temperature, the possibility of a temperature change also goes down. So this factor Rm plus Rs, okay, is almost constant. Okay, and this shunt resistance, which is made, which has to be of a very low value. Here you see that you have a shunt resistance. The picture of this here. This is not a usual resistor. This is a 50 milli, not a milli, yeah. So this is a 500 amp 50 millivolt resistor. Okay, so you can see that this is less than it's probably it is in the range of say few micro ohm resistance. Okay, so this would mean that we have a very low resistance which is capable of taking a very high value of current. However, the material that is used to make this resistor, okay, is something, is a special one. Say an example is like a material called as magnanin, okay, which has these combinations and whose resistance changes by a very insignificant amount of time, which change in temperature. Okay, so only the resistance changes only by this factor. So even if the temperature changes by 100 degrees, okay, it's going to give only 1.5 into 10 raised to minus 4 parts change in the actual resistance, which would mean that the error that is there, that are error that can be caused due to temperature, due to the heating of this shunt resistance or the meter resistance, that becomes negligible. Next, obviously, when you have a choice of an instrument where you have a shunt, you can increase the possible number of shunts. Okay, you can have multiple options for the shunt resistance, and possibly we can select between these different options by a switch. Okay, of course, this configuration is going to give us a multi-range DC ammeter. Okay, now so for example, you would have 1 plus Rm by Ri. I is 1, 2, 3 or 4. You have 4 ranges depending upon 4 values of the shunt resistance. But is this circuit actually okay? Is there any problem in this circuit? Okay, let's look at the question of what happens when the switch is between two of these when this switch is between two of these parallel resistances, shunt resistances. Okay, so let us see what would be the situation when you are switching from point 2 to point 3 and the switch is in transition. Okay, now in this situation, what is going to happen is that the entire current is flowing through this PMMC meter. Okay, and this excess of current is going to sort of blow off this meter. So this situation should be avoided. Okay, so how to avoid this situation? Okay, and still be able to switch from one to another. Okay, one possible solution is to use a different sort of a switch. Okay, we can use a make before break switch. So the switch is the head of the switch, the wiper of the switch is of a different configuration. You can see the wiper here. Okay, there are two contacts here. You see the wiper looks like this. Okay, so it is made in a manner such that at any point of time, at least one of these terminals is being touched by the switch. So for example, when it is at 3, this is the configuration. when it is a 2, this sort of would be the configuration. Okay, and when it is in between 2 and 3, you have something that looks like this, not exactly like this. Okay, so you have terminal 2 here, terminal 3 here, and it touches both of them. Okay, so it should mean that it makes a contact before it breaks another contact, and hence the name. And in this case, there is always a shunt resistance, so the risk of the meter blowing up doesn't arise. Okay, an alternate is what is called as an Ayrton or universal shunt, okay, which uses a normal switch, however avoids this no shunt condition. Okay, and this is the configuration. So you have a branch with multiple resistances, and at any point of time a part of this branch is in series with the meter, a part of this branch is in parallel. Okay, and the better part is that when this switch is in between two of these terminals, it is a supply that gets cut off from the meter. So again, there is no risk. Okay, and so in this case, when it is at 1, you have R1 being in parallel with R2, R3 and the meter, and so on and so forth for the other two positions also. Okay, now this same PMMC meter can be used as to realize a voltmeter function also. And as we know that the characteristics of voltage and the characteristics of current are like dual to one another. Okay, so in case of increasing the range of an ammeter, we use a low value shunt, okay, in parallel with RM. Okay, in case of voltmeter, you are going to use a high value series resistance, of course in series with RM, a multiplier resistance in this case. Okay, and of course and the multiplying factor will also come out to be very similar to the case that we had with the case of an ammeter. So instead of RM by RSH in that case, you have RS by RM in this case. Okay, now in the ammeter case, when we talked about the sensitivity of meter, we saw that it depends only on the multiplying factor and the other factors like the meter constants G and K. Okay, however, in the case of the voltmeter, we see that the voltage across the meter, okay, if we go back, in case of an ammeter, the current through the meter, okay, so IM was proportional to, rather, let's again go through this. In case of an ammeter, theta was proportional to IM, okay, and that was proportional to I. Nothing, and the current, the relationship between theta and IM was determined by K and G, and the relationship between IM and I was determined by your shunt resistance and your RM. Okay, all of them being constant. Okay, and of course, this part of the relationship didn't involve the shunt resistance. Okay, the theta to Im didn't involve the shunt resistance. However, when you are trying to find it, okay, when you are trying to use the same circuitry to realize a voltmeter, okay, the voltage across this terminals, okay, is going to depend or rather the current through this meter, okay, is going to depend upon the voltage across this, okay, and that will again depend upon what was the multiplier resistance, okay, because the voltage across this meter, okay, is going to be divided, as the total voltage is going to be divided across this multiplier resistance and this meter. So the voltage across this meter, okay, is going to be influenced by the amount of resistance in the circuit. Okay, so which in turn would mean that the sensitivity of a voltmeter is going to depend upon the resistance in the meter circuitry. Okay, thus if so to represent this voltmeter sensitivity, okay, we will not be able to represent it in the case like say so many degrees per volt. Okay, what we would use is the amount of resistance that needs to be present in the circuit to have full scale deflection. So thus if IFSD is the full scale deflection of the meter, then 1 by IFSD gives the voltmeter sensitivity. Okay, and so in other words, in case of a voltmeter, okay, the sensitivity doesn't relate the deflection to the voltage directly, rather it indicates the resistance required to produce full scale deflection of current of the PMMC meter when the maximum or the rated voltage is applied across the voltmeter terminals. Okay, now let's say you are using at a voltmeter as a voltmeter and there is a resistance RV and this is an ideal PMMC meter. Okay, so this entire circuitry is my voltmeter. Okay, and of course it is connected in parallel to some circuit, okay, that is getting powered by some voltage source E, and there is a resistance R here. Okay, now if the current flowing through this branch, let's say this IV, okay, is not negligible, okay, if it is significant, okay, then some power, non-negligible power, is being consumed by this voltmeter, and hence the voltmeter starts loading the circuit. So this is one of the effects, and the only way to counteract this effect is to have the resistance of the voltmeter, okay, to be much greater than the resistance of the circuit across which the voltmeter is planned to be connected. Okay, so one thing is that, so this, as a consequence, what you will have is that if you want to measure voltage in high resistance circuit, okay, then you need to configure appropriately. Okay, later in the course we will be looking at some cases, some circuits where the resistance is high and appropriate configurations or modification of the configuration so that the voltage or the resistance measurement even can be done appropriately. But in usual cases, if you don't want the loading effect to happen, the resistance of the voltmeter should be much greater than the resistance of circuit which you want to measure. Okay. Similar to the ammeter, a temperature effect can also be present in the voltmeter, and similar to the ammeter, a swamping resistance can be used in series with the meter to make the voltmeter to be more robust against temperature variations. Okay, and again, similar to the case of an ammeter, a multi-range voltmeter can be designed, and again a rotary selection switch can be used. However, since the problem of the connection or the total current flowing through the meter is no longer present in the voltmeter, because as the entire connection breaks when the switch is between two positions. Okay, again use the rotary selection switch itself. Okay, you need not the make before break switch or some fancy arrangements are not necessarily needed. Okay, however, there is one small issue here. Okay, let's say that you have four ranges. Okay, and you need R1, the multiplying resistance actually has to be multiple times. Okay, let us say that if you have a say 100 ohm resistance here and Rn. Okay, and you are having a set of multiplying resistances in a manner such that, let us say, if R1 is say 900 ohms, I am just arbitrarily putting it. Okay, let's say this is 1900 ohms, this is 4900 ohms. Okay, this is 9900 ohms. Okay, so the total comes out to be 1k, this would be 2k, this would be 5k, this would be 10k, giving a multiplying factor of say 10, 20, 50 and 100. Okay, this all looks good, but you need to have high value resistance here. In fact, in the actual cases, these multiplying factors may be much higher, and your resistances here are also of high value. Okay, so the takeaway point is that in this configuration, what you are having is multiple high value resistances and one multiplying resistance for every selection. Okay, but you can use a arrangement that looks like the atom arrangement, okay, to avoid this problem. Okay, now consider this configuration. You still have 100 ohm here. Okay, you still have 900 ohm here. Okay, but the second resistance is only 1k. Okay, this is another 4k, this is another 5k. Okay, you're not using any resistance that is 9.9k here. This total one comes out to be 9.9. No, this is 2, this is 3k. Okay, the total comes out to be 9.9k here. Okay, so you can have this arrangement and avoid using high value individual series resistances also. Okay, now that was the case where the PMMC meter was used to measure DC currents and DC voltages. The same instrument can be used as an ohm meter also, and we can measure resistances. Okay, the simpler configuration is a series ohm meter. Okay, so in which case the unknown resistance is connected in series with the PMMC meter across a known power supply, and the standard multiplying resistance R1 is also connected in series with the meter. Okay. Now if you look at the mathematics of it, the meter resistance now is the ratio of the battery voltage and all the resistances put together in series, and from which you can calculate what is the unknown resistance using this formula. Okay, of course, we have the deflection in the PMMC meter being proportional to Im, and the relationship between Rx and Im is not going to be linear in this case. Okay, and if you look at the scale, we can see that when Rx is infinite, okay, Im is 0, so at the low end you have infinite resistance, and similarly when Rx is 0, then the maximum deflection happens. Okay, so 0 deflection at open circuit and full scale deflection corresponds to 0 amps. 0 ohms. Okay, and half scale deflection, so full scale deflection IFSD, okay, happens at EB by Rm plus R1. So I half scale is going to mean that Rx is equal to Rm plus R1. Okay, so half scale deflection happens when the unknown resistance is equal to the internal resistance of the ohm meter. Okay, however, there is one important factor. The factor is that the reading that we are getting is actually dependent on EB. Okay, we are assuming a value of EB and calibrating this scale. Okay, so the indication theta, okay, depends upon EB also. What if after some time, as time goes, the battery voltage decays? Okay, what if the battery voltage decays or varies? Okay, so the battery voltage is decreasing. To maintain this EB by Im ratio, okay, we need to decrease the overall resistance. So you to have the same Rx, if EB decreases, Im decreases, so this Rm plus R1 should also decrease to get the same deflection for the same unknown resistance. Okay, now how can this be achieved? Of course, you need a adjustable resistance to compensate for this, and now in the circuit till now there is only one resistance that can be adjusted. Rm can't be varied, that is internal to the resistance of the coils that are internal to the PMMC meter. Rx is the unknown resistance, so R1 is the only choice for variation. Okay, now of course, so we can vary R1 in a manner such that at full scale deflection, that is when Rx is equal to 0, the resistance is when Rx equal to 0, the meter current is the full scale current. So what you have here is that IFSD would be equal to EB dash, the new battery voltage, divided by R1 dash plus Rm. So we have adjusted R1 dash so that the IFSD remains the same. Okay, now the problem with that is, what is the reading at half scale deflection. Okay, so at half scale deflection, Rx initially indicated, okay, so at half scale the Rx indicated is the original R1 plus Rm. Okay, and now when you actually have the half scale, okay, the actual Rx is R1 dash plus Rm, because that should be equal to the internal resistance of the meter. Okay, now whenever you change R1, you know what is the half scale deflection, means you know what should be Rx at the time of half scale deflection. But for each and every indication, okay, for each and every iteration, you can't hope to recalibrate the instrument. Okay, so that's a bad choice then. So changing R1 is a bad choice. Okay, you can adjust the full scale deflection, but at half scale you are going to end up with a problem. Okay, and to address this, you can modify the series ohm meter. So instead of making R1 to be variable resistance, you have R2, another resistance that is connected in parallel with this meter. Okay, and that is variable. Now in this case, as without loss of generality, you can assume that R1 is much greater than Rm. So R1 plus Rm is approximately the same as R1. Okay, and adding this variable resistance R2 in parallel to Rm, now when AB is shorted, okay, the total current IB is EB by R1, okay, because R2 plus R2 parallel Rm is actually less than Rm itself, and of course this when added with R1 is going to be approximately the same as R1. Okay, so the meter reading now is given by this expression. Okay, and now at full scale deflection, you can choose R2, you can tune R2 such that at full scale deflection the correct reading is the at full scale deflection is registered when AB is shorted. Okay, however, when you have a half scale, now the point is that when there is a half scale deflection, okay, the reading at the half scale deflection is mostly dependent, okay, so half scale deflection is going to happen when RH is the state when Rx is equal to R1 plus R2 parallel Rm. Okay, the resistance at half scale deflection is this value, and this value is always approximately equal to R1 now. So there is not much of a change here. Okay, in the earlier case, since R1 was changing and R1 was anyway a large component, okay, in the earlier case you used to change R1, but R1 was a large component of this meter resistance or of the ohm meter's internal resistance. However, in this case, in the modified series ohm meter, okay, R1 is not being toggled at all, so the half scale deflection is going to occur at the same or approximately the same value of Rx. So the rescaling, okay, or recalibration of the ohm meter scale is not necessary now. Okay, a alternative to the series ohm meter would be a shunt ohm meter. Okay, and as the name implies, in the shunt ohm meter, the resistances, or the resistance, this is unknown, Rx is connected in parallel with the PMMC meter. Okay, and when compared to the series ohm meter, here the scale is reversed. That is, at 0 ohm there is zero deflection, and at open circuit, at short circuit there is zero deflection, and at open circuit you have full scale deflection. Okay, and however, like the series ohm meter case, here too the scale is still non-linear. However, the scale points are reversed in the case. Let us go into the mathematics of this. Now, when the circuit is open, when Rx is infinity, the full scale deflection happens. Okay, and so from this we can configure R1 to be this expression. Okay, so depending upon the value of EB and IFSD, you can choose the value of R1 such that the full scale deflection happens at the open circuit. Okay, and for any arbitrary value of Rx, okay, the total current that is passing through the meter is given by this particular expression, and it is actually nothing but this is the total current that passes in the circuit, and Im is only this part, this fraction of the total current I1. Okay, now for half scale deflection you need Im by IFSD to be 0.5. Okay, so from this we can say that this expression should be equal to 0.5, and if you try to find out what is the value of RH, that is the half scale deflection, okay, the resistance at half scale deflection, you will see that the RH is approximately equal to Rm, because this is just a parallel combination of R1 parallel Rm. Okay, and since R1 is much greater than Rm, this is going to be actually just equal to Rm. Okay, and again it is independent from R1, so it is again robust. So you can tune R1 such that the full scale deflection happens at open circuit, and rest assured that the half scale deflection or the other points in the circuit are not really affected. Okay, and due to this case, the shunt ohm meter is actually robust against variations in the battery voltage. Okay, and coming to the references, again, like the case with the previous lecture on analog DC measurements, for this lecture too, you can you can still refer to chapter 8 of AK Sony. It's a chapter that deals with analog ammeter, voltmeters and ohmmeters. Okay, and have some read of that. Okay, with that we come to the end of this lecture. Okay, thank you for your time.